So first, in order to do that, we have to talk about movement of substances again. Now, you guys will recall in a previous lecture, in the last block, we talked about the movement of substances in terms of diffusion, but we talked really about it in terms of uncharged substances. And that is, in fact, only half the story. And you have a lot of charged materials in your body that also have to be transported across a membrane, often through channels. And often what we're talking about are ions, elements that are charged and solubilized in solution, like sodium ions, potassium ions, chloride ions. Those can be broken up into two groups. Anions are the negatively charged ones, like chloride. Cations are the positively charged ones, like sodium and potassium. Okay? Anions are negatively charged substances, cations positively charged. These things move through Fick's law, just like we said in the last block, but they also move because of electrical forces. Negative charges are attracted to positive charges, and they tend to want to move toward positive charges, and vice versa. Negative charges are repelled by negative charges. Positive charges are repelled by positive charges. So that will inhibit movement, and the attraction will assist movement. So that has to be accounted for in addition to regular old diffusion. Okay? So here are rules for solutes. Uncharged solutes will eventually, if they're membrane permeable, they will eventually have the same concentration on both sides of the membrane. If X is permeate to the membrane, you have so much X on the outside, so much on the inside. Eventually, the first thing you do is you move X and you make those concentrations the same. Okay? Impermeant solutes, if you add them all up and determine the osmolarity, will have the same concentration on both sides of the membrane. And that happens through the auspices of water movement and osmosis. And we talked about that last block. Okay? In this case, you total them all up, determine the osmolarity on each side of the membrane. Water moves to make that osmolarity the same. Electroneutrality must be maintained. So what that means is that, generally speaking, for every positive charge inside or outside a charge, there must be a negative charge inside or outside of a cell to neutralize it. Okay? And this is a very good approximation to reality. There is a very, very negligible difference across most membranes. And that negligible difference, the imbalance between positive charges and negative charges, generates the voltage difference across that membrane. So I might have a slight excess of positive charges on the inside of a cell membrane. And when I say slight, I'm talking about like 0.001% of the total number of ions. You could not measure that with any chemical means. But that imbalance, where you have more positive charge inside than outside, generates a voltage across that membrane. And but otherwise, that is a very good approximation to reality, and electroneutrality must be maintained. All right? The resting potential is that voltage across the membrane when no action potential is firing. In a typical muscle cell, it's about -90. In a typical nerve cell, it's about -70, all right, millivolts. And what that means is that that membrane voltage is the voltage inside the cell relative to the voltage outside the cell. So if a voltage is negative, let's say at -70, that means there's more negative charge inside and more positive charge outside. And the inside is negative relative to the outside. Okay? That is by convention. I did not make that rule up. It was made up probably sometime in the 1950s. And it's too late to change it now. Though some of you may think that it should be by the time we're done. Okay, so that resting potential is established by ion gradients generated by pumps like the sodium-potassium pump across the membrane. All right, and what you get are ion gradients across the membrane. You know that we have high sodium on the outside, low on the inside. That's an ion gradient. And that, combined with the permeability of those ions to the membranes, which means the number of open channels for our purposes for the most part, will determine what the resting potential is. And when that permeability changes, you generate an action potential because you change the voltage. And I know that is a bunch of gobbledygook that I just spit out. That means nothing to you, so I'm going to try to make it mean something to you now. This is what's called a cell concentration model. We have two sides of a membrane here. This is the I side, let's say, inside, and this is the E side, let's say, outside or extracellular, all right? And right now, that membrane is not permeant to any ions, okay? There are no channels open. So now, let's open some channels, but only potassium channels. So now this membrane is only permeant to potassium, not chloride, okay? Well, there is a gradient for potassium across that membrane. It's high on the I side, low on the E side. So we all know that through the process of diffusion, potassium is going to go from high concentration to low concentration, and it's going to move from I to E. Now, here's the trick. As that happens, the outside, the E side, becomes positively charged, because I have an excess, a very slight excess, of potassium on the outside relative to the inside now. And I also have an excess of chloride inside relative to the outside now. I mean, it's not balanced either. So what we have is a voltage setup such that we're positive on the outside, negative on the inside. We would say that that's a negative voltage across that membrane. Now, as the positive charge is generated here, and as this potassium moves more and more across, and more positive charge accumulates, and that voltage gets bigger and bigger, more negative and more negative, this positive charge is going to repel the potassium, which is also positively charged. So despite the fact that there's a concentration gradient there, that potassium is not going to want to move from I to E. So the more potassium moves from I to E, the more positive charge you have on the E side, and the more the potassium is repelled, and the less it wants to move. And eventually you get to the point where there's so much positive charge on the outside that potassium won't move anymore, despite the fact that that concentration gradient is still there. We've moved, let's say, 0.0001% of them or something, all right? Concentration gradient's still there. But now I've got enough positive charge on this side of the membrane for the potassium to not diffuse down its gradient anymore because positive charges repel. Okay. So what that means is I've generated a voltage across this membrane by simply having a potassium concentration gradient across it, and by opening up some potassium channels and increasing the permeability to potassium. Okay? And that's how voltages are generated. See the potassium, less and less of it wants to move, and eventually it stops. Okay? Now, when that happens, we have an imbalance of ions across the membrane, and what you find out is that they line up across the membrane like this in sort of a double bilayer. Right inside and right outside the membrane, you'll find those charges lined up. And in the rest of the cell, there's a negative ion for every positive ion, and electrode neutrality is maintained. Okay? And we're talking about a very, very small proportion of the ions here. Okay?